Hello everyone, June 17th. Alright, let's take a look at today's question. Number of increasing paths in a grid. You're given an n by n integer matrix where you can move from a cell to any adjacent cell in all four directions. Return the number of strictly increasing paths in the grid such that you can start from any cell and end at any cell. Holy crap. A total number of strictly increasing paths. Two paths are considered different if they do not have exactly the same sequence of visited cells. Oh boy! The total number strictly increasing. Path of length 1, of length 2, 1, 3, 1, 4, 3, 4, and 3. Holy crap. Look at this. OMN log MN is the longest we can expect. So yesterday was DP, so I'm suspecting today might also be DP, or something similar. And you're trying to get from anyone to anyone, and this example is really poor. Don't allow too much place to go for. 1, 1, 3, 4, right? So we're saying the number of strictly increasing paths connecting. So basically just the total number of strictly increasing paths. That doesn't really matter. And it can go 4 directions. What do you think? I mean, the most common, I say dpij, right? That's not right. Because dpij is starting. Okay, we can say the total number of like paths starting from an ij, starting from this, like when we count how many totals are there. So what we're gonna do is just to add all of them together. Okay, now we ask question, how do we calculate dpij? For example, if we have to do dp 0, 0, right? We say we want to find all the paths that's starting from this and it's strictly increasing. And then to find that, because we're here, right? This is where we are right now. And it can go this or this. So basically we need to find all the strictly increasing, and we say we're coming here to see, oh, if this is not strictly increasing, then we cannot go this way. So it's a total number of this, right? So this is actually equal to dp a 1, 1. But we also need the previous value, right? Pre is 1. Maybe I should say dp, something like this. Pre. This is actually inspired from yesterday. Right, so we're gonna start with this. This shall be this plus dp. This is 0, 1 and 1. And dp 1, 1, 1 is this because equal. So this is actually equal to 0. This is equal to 0, right? And we're gonna compute this. Right? So this previous is 1. We actually don't need. No. How about just this? But then how do you know this? We just don't go there. Yeah, we don't go there. For this, we just don't go there. We only go here. Then I can calculate this, the total number of this, okay? So now we say 0, 1, the total number of this. So dp 0, 1 shall equal to dp. Actually, that's not even 1, 1. What's wrong? That's a 1, 0. This is a 1, 1. Right, because this can go here. And that's the only thing it can go. Right, this is the only place you can go, but you can go to other places. You can go up, but it won't be able to go up because it's smaller. Right, so you can only go this position, so you go to this. And then, okay, what about dp11? Now dp11 we can go, that's smaller, that's small, so we can now go. So there's nowhere to go. So dp11, where there's no place to go, then this will become, whatever the value it is. We go 4 direction, so this one will give me 1. So this was actually gonna give me 2, because starting from here we'll have this, and have it 2, and for here we have this by itself, right, and this. So dp00 has to give you 3. Okay, so now we go this will give me 3, right? Now you'll get here. Here I say I can only do this. This is already 1. So this one is give you 3. This one actually have 2, right? This we already calculated. This is 2. This is 1. So we do 3 plus 2 plus 2 plus 1. Is that equal to, that's actually 8. We're missing 1. Which one are we missing? We got 1, 1, 3, 1, 4, 3, 4. I think the 3, wait, we counted 3, 4 already. Because of 3, we have 3 and 3, 4, right? And we have 1, 3, 4. Oh no, it is 8. Jeez, man, I thought it was 9. Okay, so let's try the next one. Next one is just 1 and 2, right? So we say we'll do dp00. dp00 is equal to 1 plus dp01, okay? And dp01 shall equal to 1. So dp00 equal to 2. So in total is 2 plus 1 equals 3. Let's give this a shot. Maybe it works. Maybe. What do you do? I need a memo. What do you want the memo to be? I want it to be a default dict. Okay. And it's gonna be default dict lambda 1. Because everyone by default is 1. And def dp is going to be ij. So this is the total number we can return in int. The total number, right? Total number. So we shall say at the beginning, not even at the beginning, we should also have m and n. Okay, so we're at ij, right? And we say, holy crap, should be int. If memo ij, okay, then we return memo ij. If not, we haven't visited yet, then memo ij starts from 1. And then we'll go for directions, right? We'll go for directions. We say for didj in 0, 1, hold on, 0, 1, 0, minus 1, 1, 0, minus 1, 0. And nj equals I plus di, j plus dj. If 0 smaller equal to and I smaller than m, and 0 smaller equal to and j smaller than n, and grid nj is larger than grid ij, then we can move to this. Then memo ij plus equal to dp nj. We return memo ij. Then we just say for I in range m, for j in range n. Maybe. I don't know. Maybe we should do this. Or mod. Res equal to res plus dpij. Return res. Alright, let's make sure that at least the first things are correct. Alright, this is going to be 8. This is going to be 3. Count paths grid. Okay, this is correct. Just submit and see how it goes. And then we can, if you want, we can do one special case. Let's see if this one passes. It does. I guess that's not too bad. Use dp, where dpij is the total number of ways to produce strictly increasing paths starting from ij. Right, and use an external memo to record result and add together dpij for each ij pair. That's mn. So this is mn. I guess mn times 4, but that's okay. Okay, let's take a look at the solution. We can sort it. What do you mean by sorting? I think this is the one I'm using, right? Yeah, this is the one I'm using. Yeah, yesterday was hard. Yesterday was hard because it's hard to find the state. That's why yesterday was hard. This one is not hard because the state is easier to find. Just ij is a state. And yesterday the state is hard to find is because you have a pre, right? I still remember yesterday's one. Yesterday is hard to, I mean, we know, we have the intuition for yesterday's. What we don't have is the ability to find the state. So, okay, that's that. We have to do this one, man. So basically, this is Dijkstra, right? It's a Dijkstra. And when you do create, so I have an idea. Actually, I already read it, and I gave it some thought. So what I think is that each time when we add a new edge, we do Dijkstra. Right? We have to do Dijkstra again, to do it again. So what I can have is the graph will set whether we need to do a new round of Dijkstra starting from this position towards everything. Okay? From one position towards everything. And then if we are asking to go starting from one position to a certain position, we can go directly tell you what its value is because we've already done the Dijkstra. So you have to build like a lot of Dijkstra basically. You have to build a lot of Dijkstra. Looking great. We need to do lots of Dijkstra. Alright, so here's the idea. I have edges, so I need a graph. Oh, let's do it this way. Build graph. Okay, self edges. And we'll return to you a default dict. A dict of what? A dict of integer and a list of integer. So for this we need a collections import default dict. Right, we say graph equals to default dict list for a, b in edges. Graph a, ooh, holy crap, this is actually a tuple of int. Why tuple? Because we have this value. So a dot append b and so it's from to an edge cost return graph. Okay, so now we can say self dot graph equals self dot build graph edges. Done. And then self dot renew, whether we renew the Dijkstra. Dijkstra. That's gonna be false. No, true. At the beginning is true. Everybody needs to renew the Dijkstra. Times n. Probably need n, so let's collect n. Okay, so then what? Let's call it should renew redo Dijkstra and self.Dijkstra. What is Dijkstra? From a certain start, and we shall have a list, right? We should have a list. We shall have a list, and it's just the path. We can call initialize Dijkstra. Def initialize Dijkstra. It should be a dictionary. No, it should be a list of int. You can say Dijkstra equals to math.inf times n self.n for this in range self.n. Each one is a list. Is the longest, the shortest path to reach, and of course the shortest path to reach itself shall be 0. Actually, we can test this. Right, we can test this by doing the shortest path 3, 2. Let's just say 3, 3. Let's see if 3, 3 is equal to 0. Yeah, it's 0, right? So, shall say for I in range self.n Dijkstra I, right? It's equal to 0. Then we return Dijkstra. So this says self.initialize Dijkstra. Okay, so initialize it. Then what? Then we need to actually def do Dijkstra. Don't return anything. Let's do Dijkstra. Oh, we need to have its starting point. The start. Okay. All right. So we have the start. Now we do Dijkstra. How do we do it? Well, we do it by. We need a heap. Heap shall equal to this. How do we do it? We start from a certain position, right? And then what? We look for all its neighbors. Okay? And then we find the ones that has the shortest path currently. Okay, so the start, the queue, the heap. Now we have a heap and we have a queue. Queue. Start 0 while queue, right? We have a temp, and then what? Isn't that should be in a heap? Yeah, that should be in the heap. That should be the heap. And we should put 0 first. 0 start. Wow, heap. Okay. Hold on. Need to do very important stuff. No more double portion to that. I should have a wonderful, gorgeous dream. Love and happiness. Tomorrow feeling fully recovered. I'll make this so many it smells so good.
Right.
So soft. I love your pajamas. Alright, I'm back. I was trying to figure out how Dijkstra is done. So we shall say dist, right? And node equals heap q dot heap pop heap. If this is not equal to self.dijkstra start node. Right? If it's not equal to, we'll continue. Otherwise, it's equal to. Okay? It's equal to, then we need to go this node, then we find its children. For child in self.graph node. For child and what? Cost. Child cost. Right? Then if dist plus cost is smaller than self dot Dijkstra start child self dot new cost, okay, new dist equals dist plus cost, right? Then we say if new dist is smaller than self dot Dijkstra start child equals new dist, and then heap q dot heap push. Heap, we're gonna push in the new dist and child. Blah blah blah. Okay, done. Go back up to the heap. Blah blah blah. Once we're done, get everything done. Okay, that's Dijkstra. All right. So shortest path. Okay. from node 1 to node 2. Then we say if self dot should do redo Dijkstra, then we say self dot do Dijkstra node 1 and self dot should redo Dijkstra node 1 equals false. Okay. And every time we add edge, yeah, so this one equal to false. We already redo the Dijkstra, right? Then we shall return self dot Dijkstra node 1 node 2 and add edge. Basically we say self dot graph a b cost equals edge. So a dot append b cost, and then self dot should redo Dijkstra a equal to true, because we add an edge from a to something. Oh, hold a second. It's not just from a to something. And everybody points to a. They need to redo as well. Holy crap. How do I know who points to a? Because a points to b, right? Because there's no edge existing between a to b. Okay, so a to b has no edge. Now we add an edge from a to b. Okay, which means anything that original go to b can reroute from a. Maybe, because we're not sure, so maybe I just do this true, right? And then we should, and then this is equal to false. So every time we add an edge, we'll redo Dijkstra. No, the Dijkstra is dependent on maybe we just everybody equal to true. Everybody needs to redo it. But what if it's not related? But how do you know it's not related? Right? You add 1, 2, 3. So everything starts from 3 is not affected because we add an edge from 1 to 3, right? So everything starts from 3 is not affected. Let me think. Everything starts from 3. You add something to you and you start from this, right? You try to go to other edges and this will only lead back to you. So I do think it's not, right? Because you're starting from you want to go out. You don't use this edge, right? And the only use for this edge is go back to you. So, okay, so everything start from 1 need to change. And anything that comes to 1 need to change. Maybe I just say this and self dot should redo Dijkstra original b equals should this b, and then this b equal to original b. I don't know. Want to give it a shot? Something is not right. Which one? Well, I think it's -1, right? If the last one. Interesting. That is not expected. Okay, node 1, node 2, and this. True. And I redid Dijkstra. Interesting. Take a look at the graph. Zero, 2, 1, 5, 1, 2, 2, 3. I have 3. 2 to nothing, yeah? And I already said I want to redo. So self.do Dijkstra, we do Dijkstra again. Have a start. Start is node 1, which is 0, right? And 0, we go to oh, we didn't. We already exited. Shoot. Yeah, you're saying if you're redoing it. Okay, self.Dijkstra. Maybe we shouldn't initialize it. Maybe that shall be sufficient. Let's just do this. Save a function. And then we redo. We'll just say the extra start, the extra start. Right, and self dot the extra start 0. Nope. Oh, of course. Self dot add. Okay, it's correct, but didn't mean anything. I could time out, so give it a shot. Oh, huh. I'm not expecting this to pass, honestly. So I am surprised that it actually passed with not too bad performance. So this is actually a pretty easy one, right? Okay, so what do we say? Create this perform Dijkstra, right? Dijkstra for each node when the node is queried, right? And when we perform and when we perform Dijkstra, we do it for all reachable nodes. Right. Thus, if in the future a different query, right, a different query is needed from the same starting point, we can directly return the min dist. The addition of an edge requires all previous Dijkstras from all nodes except from the end node of the newly added edge to be nulled. To be annulled. And performed again when queried in the future. That's it. That's basically what it is. Nothing fancy, nothing too good, nothing too bad. There's lots of Dijkstra. We build a graph, it looks pretty nice. And then this is, yeah, I should say, redo Dijkstra for all starting nodes except B, right? Because the added edge from A to B does not affect the Dijkstra starting from B. So we save some time here. Right? If we should, we update, otherwise we don't update and immediate return. Okay, let's take a look. I don't think they just do the Dijkstra every single time. Huh. They already checked. Oh well. Floyd Walsall. It's Owen squared. Yeah, I'll just stick with Dijkstra for now. So basically what they do is just do Dijkstra every single time. I make it a little bit more complicated, right? I determine when the Dijkstra needs to be done. It's the same. All right, that'll be it. I mean, we did all this. Okay. That'll be it. I will see you guys tomorrow then. Adios.